A question for how to do problem 33 in the book, and I think this is a very useful one to discuss the nature of static friction. The reason that we care about this is that static friction kind of behaves in a weird limiting sense, and we want to fill it out with this problem. So if you read chapter 6, problem 33, it sets up nailing a board into a wall by pressing on the board and generates a normal force opposing that. And then there's a static friction force that keeps the board from sliding down. And the problem says if the mass is 1.6 kilograms and the static friction coefficient between the wall and the board is 0.79, what is the minimum F that I have to push on this to keep this in place? And then asks the interesting question here, what happens if I increase it? I'm above that minimum. How does that change the static friction force? So, without further ado, we draw a free body diagram. There's a normal force and a force that we're pressing into the wall with. Those are supposed to be the same size. There's a weight going down. And then there's the static friction force going up. Now, the board is motionless, so we know that the sum of the forces in the x direction is equal to n minus f, and the acceleration is going to be 0. So that means that the normal force is equal to the force that we're pressing into the board with. We also know that the sum of the forces in the y direction is also 0, because it's not moving. And defining the plus y direction, as they've given us helpfully here, we know that the static friction force minus mg is going to be 0. And then we know that the static friction force is equal to mg. And further, we have a friction model that says Fs is going to be less than or equal to mu s times the normal force. And we know from here that the normal force is equal to the contact force. So we know that Fs is less than or equal to mu s times F. Now it asks the question, what is the minimum force that we can press through? And that means that we're going to reduce our F smaller and smaller and smaller and hope that this condition that the friction force equals the weight remains true. Thus, we're going to have that Fs is going to have to be equal to mg and also equal to mu s times n. So in this less than or equal case, we ask what's the case of equality. And then we can figure out that, that's also, mu s times the force that we're pressing it in. And then we're after the force that we press it in, so we just say that F is equal to mg over mu s. I do some plugging in, so I get 1.6 kilograms. 9.81 meters per second squared, the 0.79 that's given in the problem, and I get an answer of 19.9 newtons, or I guess, yeah, to the precision in the problem, 20 newtons. Now the interesting question is, what happens if we press with a harder force? Well, that's the case where this less than or equal comes into place. The force of friction doesn't change, so press harder, harder. Fs is always going to be equal to mg. If it's not, if Fs is greater than mg, then there's a force imbalance in the y direction, and the board would shoot up. Would accelerate upwards. And that is weird. So we call weird, the fancy word for that is not physical. So we don't end up with this happening. Therefore, Fs is always equal to mg. So this is the answer to part B. Doesn't matter what F is, we only have a minimum force that we can press on it. Past that, it's always just going to be equal to mg to keep it into place. So subtle points, and it's good to understand that particular aspect of static friction.